We discussed about the boundary conditions at the interfaces between dielectric and dielectric interface. We are going to continue that same argument for the conductor and dielectric interfaces today. So, and we will see one example. By the way, you can understand how this boundary conditions help to calculate the field at different regions. So before that, we have discussed about the how this conductor uh, inside the conductor and how the field is available, and if we place the field inside the conductor itself, and how this uh, conductor behaves, and that is actually described with the quantity called conductivity. And similar way, we have another material called dielectrics. This works with the concept of dipoles of the molecular nature, and thereby we get the internal fields or internal flux density, what we call as polarization. By adding this external field and the internal field, what is induced because of the dipoles, we will get the total value of the uh, flux density, and that is equal to 1 plus psi into epsilon naught the electric field, where psi is the uh, polarizability. Always people refer this 1 plus polarizability as the dielectric constant. And we also have seen different nature of the material, how it is spreaded over the space. And we also discussed about the continuity. So the continuity equation derived based on the fundamental idea that the conservation of charges, therefore the flow is always uniform throughout the structure, and thereby we get inward amount of current is equal to outward current flow. And keeping this in mind, when we substitute this the basic the divergence of the electric field, which is connected with Gauss law, if you substitute upon the continuity equation, we will get the solution. So that describes how this charges are distributed over the structure and how they vary with respect to time. And finally, till this charge come to uniform throughout the structure, it will keep on move here and there. It is like the electric field when it is very high over the space, when it is high at a particular point. Later, after some moment, this will be dispersed over that. So it will go to high here, then it will come back. And finally, after some moment, it will become uniform throughout the structure, which we call the total time required for that is nothing but the diffusion time in semiconductor device. We will always call that. Same thing we can have in classical, that is electromagnetic theory itself, as rearrangement time. Seeing some example. Then we move to the uh, boundaries. Okay, so in case of almost every structure, whatever you see, let's say we are human, we are made up of this biological material, but next to that we have air medium, there is an interface. So between these two interfaces, whenever there is an electric field is traveling, let's say there is a mobile phone we are having, this mobile phone radiates electric and magnetic field. Whenever this electric and magnetic field travels through us and going out, there's supposed to be change in the dielectric material itself, as well as the polarization phenomena. Many things could have happened. So for this all studies, we supposed to know the basic where this electric field originate and which are the mediums it is traveling, and there its properties like the dielectric, sorry, the permittivity and the conductivity. All these information, if we know for all the materials, then we can easily calculate how the electric field available in other regions also we can find. So to do that, we supposed to be very clear about what is happening at the interface, because this interface is very common to both. Thereby, the electric field and magnetic field, whatever it is crossing, that also supposed to be equal. So in order to do that, the common method we follow. So that is what described over that. So this classified as 4 categories, but it is enough to study this basic two, where free space is going to be epsilon r equal to 1. and the conductivity equal to 0. That means there is no charge density, there is no surface charge density. Thereby, we will get the then we can easily substitute all these things. So in the last class we discussed about dielectric cases. So basic argument is there are two materials, and these material commonly share one particular boundary or surface. So by this, it is classifying the material into epsilon 1 and epsilon 2. And this boundary is defined with some mathematical expression. Therefore, we can easily get the normal to its boundary. And this normal to the boundary can classify the incoming and outgoing electric field as two components. One is the normal component, which is parallel to the normal of the surface, or the normal to the surface at the point of interaction. So this is the interaction point. Just with respect to that, it is normal. And if it is happened here, the normal will be in this particular direction. So it is very important to define the surface clearly. And with respect to the interaction point, the normal is supposed to be calculated. And from that, we can define there are two components. One is normal component and the tangential component. Adding these two, we will get the two things. Both are vectorial components. Now, same thing is applicable to this field available in the medium 2. Now, the question is, when this traveling from one medium to another medium, and these two materials are completely different materials, and assuming that the conductivity equal to 0 itself, but for both the cases, even though so, then the electric field E1 will be equal to E2 or not. That is a very important question. If it is so, the problem is solved. If it is not, then what about the value of it in terms of E1? So if the E1 is known, how to calculate the E2? So that is what actually we're supposed to finalize. For this particular case, we have divided this field component to 4 field components, 2 tangential component, 2 normal components. We are going to find the link between them. If we find the link between them, then we can find the link between this E1 and E2. So for doing this work, we are taking a very fundamental equations. One is the Gauss law, so which states that the integration of the total flux density will be equal to the total charge density. The other one is the basic Coulomb's law itself. When you integrate the electric field over a closed loop, you will always get 0. This is because the electric field is always converging or diverging nature. There is no circulation or it is not following any closed loop concept. So thereby it is always be 0. Keeping this two things, because one is actually the right hand side we have 0, the other one right hand side is not 0. So these two conditions we can easily take it into account to compute the both the concepts. And in this electric field, it is independent of the material. Either it will become E1 or E2, but this flux density will be having epsilon E will come. So this epsilon, we know that it is nothing but epsilon naught into epsilon naught. Thereby the material properties will be coming into the picture. Therefore, we will be having two different values for this flux density. For this, we have come up with a simple method. One is loop, rectangle loop method. Another one is pillbox method. Okay, so what we are doing, first we are describing the nature of the material. So the material is two material. They are sharing the common surface. And at the interaction point, we are finding the electric field 1 and electric field 2. And there we are dividing them into normal and tangential component. With respect to that, we are describing a closed loop. This closed loop will cover both the structure in an equal way. Thereby, we have section 1, 2, 3. Similarly, 1, 2, 3. Totally about 6 sections are there. And in this, half of that is in the medium 1, half of that is in the medium 2. And that is what we are describing here. So in the medium 1, we have this structure, this A to B, A to B, and this half of that, this half of that, and this C to D, this half, like that. It is all written in this way. Now we have to reach the boundary. Not to reach the boundary, we are supposed to make this del H is nearly equal to 0, which means it is infinitely small. And by considering that, we can get many terms equal to 0, and in the right hand side equal to 0. So that is what will give this equation. This tells that in both the cases, even though they are completely two different materials, their tangential component, there won't be any change. So this is described as the tangential components are continuous across the interface. But whether this is same for the flux density or not. So this is actually the statement which we have seen for the tangential component. And when we apply for this corresponding D, we can easily say that the D1 will be equal. So let's say D2T is nothing but we can bring this to here. So you will get epsilon2, epsilon1 into D1T. So this clearly says that whatever the value for D1, since epsilon1 and epsilon2 is not equal, therefore you will get other value. In other words, the tangential component of the flux density is always discontinuous across the interface. So by this, we got the expression for the tangential components. And then what about the normal component? In order to get the normal components, we are having this pillbox. The pillbox is nothing but a particular surface, a cylinder, which is kept half of that in the medium 1, half of that in the medium 2. Thereby, we can capture the normal component with respect to the surface, because this del S is nothing but the particular surface, and it has the normal component itself. So that is the interesting thing. So by capturing the field whichever is going through this, obviously the normal components alone will be going through that, and thereby we can take it out the particular one. So, and we have to integrate over that. When you integrate over the del S, since it is uniform, you will get this normal component along the particular direction, and with respect to the second component is going to be means it is going to be opposite. Thereby we need a difference, and this difference is nothing but uh, the total the difference between the charge densities, and which is defined as rho s into del s. Since the material is linear over the space, we can take this del out, del s simply we can cancel. We'll get this expression. So what this tells that if there are two material which are splitted by a surface, and the surface has some surface charge density, it is very much possible. Like if you take many junctions, PN junction, or if you take many, let's say metal and another two metal surface or two oxide materials, wherever you take, always there will be interface charges, often referred as interface charges itself. So this is what here it is referred as the surface charge density. And if this is not if it is not equal, then this clearly tells that these two value cannot be same. Therefore, this is actually discontinuous. So this normal components are discontinuous because of the charge density. There are some special cases where we will get no surface charge density, and that in that case we will get the continuous field. And this we are going to substitute or we are going to write in terms of the field component itself, and thereby we are actually getting this. So here we are, this is actually in the flux density. Now in the field form, we can write this E to N is nothing but epsilon1 E1 divided by epsilon2. This is a normal component. You can find clear difference between this two things. So this normal component, definitely both are not same. Thereby, normal components are not continuous. They will be continuous if only there is no charge density available. However, the electric field is for the tangential component, uh, it is continuous, but for the normal component, it is not continuous. And this also give the idea that how to calculate the second term. And this is actually, we have seen all the uh, we have seen that there is a clear statement that there is a interface case and it is following a particular direction. Here there is no mention about what is the angle of the uh, field with respect to the normal. If we account this, then we will get the accurate value of it. So to introduce that, there is a two angles are introduced. One angle describe the electric field with respect to E1 with respect to the normal to the boundary. So we have a boundary and we have a normal component. And with respect to that, and this particular point, there is a field is traveling. And with respect to this medium has theta 2, and this in this medium side we have theta 1. And we also know that theta 1 definitely not equal to theta 2 because of the refraction. So and so this field component, let's say this is E1 and this is E2. Considering this theta, then we can get the this component, that is tangential component, which we can easily calculate with the sine theta, because simply it is going to be the opposite side. So this opposite side, so which we can easily define with respect to sine theta, and same thing applicable to the E1 and E2 case, both the cases. Now we are going to apply the boundary condition 1. The boundary condition 1 states that that tangential components both are equal all the time, irrespective of whatever the angle it goes in. And there comes E1 E1 sine theta 1 will be equal to E2 sine theta. Now you can clearly see that this E1 and E2, how they are linked. You can clearly see that. Now, for the same thing, we can apply the condition 3 and 4. So condition 3 and 4 states that the normal components will be discontinuous even when the charge density is 0. Surface charge density is equal to 0. So now we are actually finding this normal components. Normal component, obviously, we can calculate with the cost term. So when you substitute the cost term, then when you divide this equation 1 and equation 2, then you will get interesting expression that tan theta 1 by tan theta 2 is nothing but epsilon r1 divided by epsilon r2. And this is actually later we define this as a law of refraction. And now if you multiply with, if you divide with mu 1 and here with the mu 2, you will get refractive index. So which clearly tells that the electric and electromagnetic field and the light both are almost same. And this law of refraction, which is applicable in the for mechanical waves, for example, the water wave or heat flow, for these also, we will see that there is some huge similarity will come. So that is what we can understand out of that. Yeah, next we are going to discuss about conductor and dielectric interface. So when there is a conductor, so this is a conductor and this is some dielectric material, and there is a field actually traveling from conductor and it is coming towards the it means it is propagating inside the conductor. In that case, how the components will be, whether the electric field at this one will be equal to here or not. So in order to answer that, same thing we are doing, we are actually dividing this into two components, normal component and the tangential component. And for tangential component, we are applying the closed loop method. So this closed loop method, when we do that, you will get the remaining half of that which is available inside the conductor. We always know that this electric field will be 0, which already proven in the very beginning itself. So we already proved that the electric field inside the conductor due to external electric field is always be 0. So by this, the electric field will be 0 in the conductor, and therefore out of the 6 calculations, 3 will be 0. We will get only remaining 3, and so the remaining 3 are nothing but this this with respect to so this is in the ABCD. So current flow is AB, that is del W, which we will get ET del W plus this half. So this half is actually towards the opposite side direction. So you will get minus E normal. So this is 1, E normal 1 into del H by 2, and plus you will get En del H by 2. So this obviously that these two components anyway going to be 0 because two-way both are same, they cancel each other. In other words, this del H anyway we will make it 0. By the way, this will be 0. So only this component will be left out. So that is what it is showing here, that the left hand side is nothing but tangential component 1 into del W, which is equal to 0. In other words, it tells that W is not equal, this del W is not equal to 0. We haven't made 0. Therefore, there is only one sense that T1 equal to 0. Okay. So this clearly tells that this tangential component in both the cases, it's supposed to be 0. At least in the surface, it will be 0. So inside the metal also it is 0. In the surface also it is 0. So therefore, this tangential components, there is no other go. According to the law of conservation, they are supposed to be reflected back. And what about the second one? The second one is we are going to apply the Gauss law. We will use the pillbox. So the pillbox will be exactly placed such a way that we will capture the normal component. So here also we are applying that, and we will consider there is a surface charge density, and you will get there is a normal component, which is nothing but surface charge density itself. So there comes directly the when this charge density is equal to 0, normal component also will be 0. In other words, we have a conductor. The conductor has some surface charge available, and there is a field component is coming. Let's say this is E1 component. It has two components. One is tangential component and the normal component. This tangential component, irrespective of whether it has charge density or not, it is going to be discontinuous. In other words, it will be simply reflected back without any problem. But what about the normal component? This normal component will be reflected back, but with a condition that subject to the surface charge density. So if there is a surface charge density and the surface charge density describe the reflected field component. So this is what we can understand from the conductor dielectric interface. The same theory could be applied for the other case, that is the free space case. So if we place the conductor dielectric with respect to the free space, you will get the second medium, that is epsilon R2 will be equal to 1. And by doing that, you will get the very similar behavior of the conditions, boundary conditions will come. Let's take a simple example so that you can easily understand how to calculate this field components. For this, you're supposed to remember the boundary conditions. And the second thing you should know that how to take the how to calculate the normal and tangential component. So there are two extensive homogeneous isotropic medium is available. This homogeneous isotropic medium means throughout this region you will get uniform dielectric constant and conductivity. And isotropic means like in both the directions you will get the same dielectric properties. There is no change. So homogeneous itself already means that. So now they meet at, there are two mediums, and these medium is actually meeting at z equal to 0 plane. And for just above the z equal to 0, we have dielectric constant 1, and we have dielectric constant 2 in the other side, which is the value is also given. Now there is a uniform electric field exists in the medium 1. So in the medium 1, we have the electric field 1, and its value is already given. So here you can see that. Now we have to calculate this E2 in the region. So what is this E2? And we have to find the angle created by the E1 and E2 with respect to the interface. So with respect to the interface, what is the angle of the E1 and what is the angle of the E2? So since there is a continuous and discontinuous fields, always there will be a completely different angles will be there. If both the dielectric constant are same, then interestingly we will get that. And the energy densities we can easily calculate by taking this the electric field square 1/2 of that. So then we will get the charge density. So we can easily calculate that for the given structure. And I think we haven't calculated this energy densities with respect to electric field and magnetic field. So maybe you can ignore that. Okay, the very first thing we have to do is these all boundary conditions are written in terms of the tangential component and the normal component. So for this case, we're supposed to divide the given input into normal component and the tangential component. Therefore, we're supposed to know what is this normal component. The normal component is, or the normal vector is nothing but the normal to the boundary. So here the boundary is uniform along the z equal to 0. Therefore, the normal component is supposed to be this az vector itself. And the remaining terms like ax plus ay vectors are nothing but tangential components. So in order to isolate the normal component, the best idea is you just take the E1 vector and multiply with this normal vector, and you will get only this normal vector's magnitude around will come. And take this magnitude and multiply with the normal vector, then you will get the E1 n will come. So this is nothing but the normal component. So it is very, very simple. And the remaining components obviously will become 0 by the dot product itself. So how to do that? We are actually going to, first of all, we are going to take the normal component, which is az vector, and we are going to multiply this E1 vector into the normal vector. So E1 vector into this, you will get the magnitude of the normal component will come. For the medium one, you got it. That is 3. Therefore, by multiplying the unit vector, you will get the normal vector. And if you subtract this, so we already know that E1 is nothing but E1n plus E1t. Therefore, E1t will be nothing but E1 minus En vector. So this look very childish, but you have to write all of them in vectorially so that you need not to worry about all your calculations. They always will come correct. So the easiest, so therefore we can easily calculate this tangential component. The tangential component is nothing but other than the normal component. We can isolate that. So now we have isolated this normal component and the tangential component in the medium one. Now we can apply the boundary condition. The first boundary condition is that both the tangential components in both the mediums will be same. Therefore, the second tangential component is equal to the first medium's tangential component. By the way, we got the same result itself. Now, what about the normal component? The normal components are defined with respect to this Gauss law, so which is defined as the two mediums flux density difference will give us the surface charge density. But as of now, here it is mentioned, there is no mention about conductivity, or there is no mention about the so-called surface charge density. Therefore, we can assume the surface charge density is equal to 0. So you have to write that since there is no mention about surface charge density, we are going to take is equal to 0, and this will give this value, and we can easily get that the flux densities are continuous. Now we are going to substitute for both the expressions, that for the medium 2, for the medium 1 we are writing, and we know this normal component, we know the value of first medium's dielectric constant, second medium's dielectric constant. Therefore, we can calculate the value of this second normal component, which is written over here. Now we have to simply substitute all the values. You will get the value this. So you got the normal component or the medium. So you already have this T, this electric field, the tangential component, normal component. When you add them, you will get the E2. So by the way, you got the E2 vector. So for the given E1 vector, we have calculated the E2 vector. Now we know both the E1 and E2 vector, and we also know how to calculate the magnitude of that. We have to take the root of, and then we have to means the sum of all the magnitude squares and take root of, you will get the magnitude of the E1 and E2. Now the second calculation what we are going to do is we have to calculate the angles created by E1 and E2 with respect to the interface. So here the angles created with respect to the interfaces are assumed as alpha 1 and alpha 2. If it is clearly visible here. So this is the interface. So here we have the interface, and in this with respect to the interface, this E1 vector and E2 vector, they are going to produce alpha 1 and alpha 2 respectively. And if you want to, it means in order to compare with respect to the normal, they are actually producing theta 1 and theta 2. And by the way, we can easily get the link between that. But the boundary condition what we derived for the arbitrary angles, we already know about it. Okay, we already know about in terms of theta, we know that. So that is why it is converted into theta. Later we can calculate this angles. So we have this two normal components and the tangential component. When you take the ratio, then you will get the normal component tangential. And by the way, you can easily calculate the tan of that. The tan of that is nothing but tangential component divided by the normal component magnitudes. These two magnitudes, you will get the value here. So you got the tan theta. So by the way, theta 1 value you can easily calculate. Since theta value is known, when you substitute in the equation 1, you will get the alpha value. So this is very pretty simple. And the second one, we can do the same way. You got both the normal components of normal component and tangential component, both are available. And you are going to take the ratio of them and you can do that. The same calculation we can do with other way by this is one way. Otherwise, if you know the magnitude of the E1 and magnitude of the normal component, you can take the ratio there. You can directly get the tan itself will come. Sorry, cos theta 1, cos theta 2 will come. That also you can do that. That is up to you. So by the way, we can easily get the theta 2. And so theta 1 is not equal to theta 2. This clearly tells that if this is the normal to the boundary, this is the boundary, normal to the boundary, and there is an incoming signal, let's say with the electric field of angle approximately 30 degree, and it is reflected and with about 53 degrees. So it is because of the dielectric constant with the difference of just 1, because one has the dielectric constant of 4, the another one has the dielectric constant of 3. Because of this, that is a great change. And these angles largely influenced by the electric field also. The magnitude of the electric field also largely influencing that. And of course, it is satisfying the law of diffraction. And we can take the energy stored in the medium 1 and 2 by simply doing this simple exercise 1/2 epsilon 1 E1 square. We already know the magnitude of the E1, which is nothing but root of that. So the magnitude of E1 is nothing but root of all the magnitude squares. So in order to take the square, you can remove this. That is what it is done over here. And all the calculations beautifully substituted, you got the energies available. You can see that the energies are not same. That means this energy is dissipated in some other direction. So this could be possibly, it is assumed that whenever there is a discontinuity in terms of medium, that medium 1, medium 2, and a field is traveling with a E1 and it become E2. And when it is moving from one medium to another medium, due to the presence of charge densities, or these charge densities are nothing but the discontinuous electric field, which are left over because of the difference. So by the way, so these are two theories. One is the charge density is responsible for the discontinuity, or the discontinuity is responsible for the production of the interface charge density. In either way, it clearly tells that there is a surface charge density. And the interesting thing is these all works were being done well before the theory of quantum mechanics. Later, the same theory being proved with quantum theory also. And with that only, we are actually arguing upon various devices like the whenever we apply gate voltage here, we know that there is a accumulation of charge. Do you know what is this region is called? Anybody knows that? So you haven't studied MOSFET in your over the last semester? Yeah, please.
Depletion region.
Yes, correct. That is called the depletion region. And there are theories like this depletion region happens because of attraction of charges from here to here. But before applying the field itself, there existence of some charges. So, and the same theory, when you write in terms of energy band diagram, with the, let's say, conduction band diagram, when you draw, then you will get this kind of charge. So there is already existence of the electric field even before the application of the field itself, which we call equilibrium. So this is actually the interesting concept that the quantum theory, sometimes the question will come, quantum theory is really needed or not. Of course, it is needed in some special cases. But most of the works which were being done before 1950s, they worked with this simple electromagnetic field theory itself to solve most of the current problems, voltage problems. Even Kirchhoff's law entirely works with classical mechanics only. There is no quantum theory required for that. Even recently, some papers are coming that how this Kirchhoff's law could be used for quantum circuits or quantum phenomena. The same example is given with another exercise problem. The answer is also available. Try to work out and check your calculations, and I will help you to do that. Well, I will stop now here. So by the way, we have completed the module